Now we have come to my favorite topic in all of algebraic trig identities. As you can see over here, there are so many different identities, and this is just the ones that we are learning. Again, don't be daunted. All of these formula will be in your formula booklet. The ones labeled SL are just for SL, and the rest are for HL only. Now let's zoom right into it. The first section of trig identities are the reciprocal identities. First of all, we have tangent x equals to sine x over cosine x. If you remember this from a previous video, I talked about this. Next, we have secant x equals to 1 over cosine x. And the next one is cosecant x equals to 1 over sine x. How I remember this is that secant will switch to cosine, and cosecant will switch to sine. So that's just to help you remember cosecant x equals to 1 over sine x, and secant x equals to 1 over cosine x. And lastly, cotangent x equals to 1 over tangent x. Next, covering the Pythagorean identities, which involve all these squared things. Look at it, all of these are squared. So anything squared, look at the Pythagorean identities. First of all, sine square x plus cosine square x equals to 1. 1 plus tangent square x equals to secant square x. And 1 plus cotangent square x equals to cosecant square x. By the way, right, sine square x is the same thing as saying sine x whole thing squared. These two are the same thing. So secant square x is just 1 over cosine square x. Next is compound angle identities. Here I have sine a plus minus b equals to sine a cosine b plus minus cosine a sine b. Next, I have cosine a plus minus b equals to cosine a cosine b minus plus sine a sine b. Now the plus minus and minus plus here just means that if I have, let's say, cosine a minus b, what this will be equals to is cosine a cosine b plus sine a sine b. So this minus plus just indicates a switch in the sign. If you have plus here, you have a minus here. If you have minus here, you have a plus here. And this is the tangent compound angle formula. The final one, double angle identities. Sine 2 theta equals to 2 sine theta cosine theta. Cosine 2 theta equals to cosine square theta minus sine square theta, and all these. Usually, the most important two is this one and this one. When we want to replace something in terms of cosine theta or just sine theta. And finally, we have the tangent double angle formula. Now, before I continue, one very important thing I want to note is that x can be substituted for anything. So I can have sine square 3x plus cosine square 3x. This is still equals to 1. I can have sine 6x, and this is equals to 2 sine 3x cosine 3x. This is using the double angle identity. Now, I just want you to be cognizant of that, because whenever you're solving questions related to trig identities, that is a very important concept. Now, before we start proving trig identities, I have 2 tips for you. It is useful to simplify everything in terms of sine x and cosine x. If you're stuck, try to simplify the other side. Always keep your end goal in mind, and I cannot emphasize this enough. Always keep your end goal in mind. Let's do this question. Prove the identity tangent x over 2 equals to sine x over 1 plus cosine x. Usually stuff in terms of sine x and cosine x means it's simplified already, so we always want to start from the more complicated side. That will be the left hand side. In this case, complicated just means there is more to simplify. So how would I simplify tangent x over 2? It is useful to simplify everything in terms of sine and cosine. Let's use this identity. And also, if you realize something, this kind of looks like this somewhat. It's in a quotient form. It's a lot closer to our end goal. So that will probably help us. So if you see, we have tangent x over 2 here. If we replace x with x over 2, this becomes sine x over 2 and cosine x over 2. Okay, now at least we got a quotient, which looks like this quotient over here. There's one thing though. The angle here is x over 2 and the angle here is x. How do we change this? Now, due to the sheer number of formula we have to use for this question, this is probably a slightly harder question. I'll rate this at probably a 5 to 6 marks. When it comes to trig identities and later on integration, I feel like the most important thing you have to do, other than using these tips, is to practice. See how to use these formulas in different ways, and then you'll be really good at solving trig identities. So actually, we can use this in the double angle identity somehow. if we replace 2 theta with theta over here, so cosine theta will be equals to 2 cosine square theta over 2 minus 1. And will also equals to 1 minus 2 sine square theta over 2. In this case, I can convert sine square theta over 2 will be equals to 1 minus cosine theta over 2. And cosine square theta over 2 equals to 1 plus cosine theta over 2. Again, whenever you see half angle, it is useful to convert it back, provided that's what you need to do for the end goal. So that's what we'll do. We'll simplify sine theta over 2 to square root of this and cosine theta over 2 to square root of this. And from here, I can cancel out the 2's over here for us to get this over this. Now again, we're kind of a bit stuck. We have surds here, but we don't really know what to do. What I like to say is, always keep your end goal in mind. What's your end goal? Sine x over 1 plus cosine x. Oh wait, 1 plus cosine x, doesn't that look familiar? What can I do? To get this 1 plus cosine x in the denominator, what I can do is multiply by square root 1 plus cosine x on the numerator and denominator. Now if we multiply this top part out, let's combine the surd. We get square root 1 minus cosine x, 1 plus cosine x, which looks like difference of 2 squares. So let's simplify that to 1 minus cosine square x. Now if we look at this, what we want to refer to is all the Pythagorean identities, all the ones with squares in them. And we see 1 minus cosine square x is just sine square x. So we see this as square root of sine square x. And this is just simplified to sine x. And you see, this is the same as our numerator. And with that, I've proven this identity. Thank you so much for watching. I hope now you have a greater understanding of how to use trigonometric identities.